slides are.
Gotta remember what you wrote.
So
It's been like a month ago. Where's all the pictures? Oh wait, this is a theory paper. There's no pictures. There's a picture.
Okay.
Right, you know what you're gonna say?
And
Just try to fill 8 minutes. 6 minutes minimum though. I'm not starting until you play, or until you talk. Okay?
yeah. Alright, so my project deals with quantum processors and quantum computers. But first, before we begin with that, what is even a quantum computer? So you know, like a classical computer, it has these things called bits. Now bits are the little tiny building blocks of quantum, of a regular computer. But what's a qubit? Now, say you have 2 bits. 2 bits of information, it's either 0 or 1. So you have like 0, 0, 1, 1, etc. To determine what state you're in, you need 2 numbers. It's either the first one or the second one. It's either 0 or 1. But when we transition to this quantum bit, you have 0, 0, 0, 1, 1, 0, 1, 1. You would need to know 4 different numbers to classify the state. And this is only for two bits and 2 qubits. So if you go like for 3, you only need 3 numbers for the classical one. But then you're going to start to see that in a classical sense, 3 qubits corresponds to 2 to the n regular bits. So for 3 qubits, it's actually 8. 2 to the third is 8 classical bits. And if you keep going with that, you're going to see that it's exponential, 2 to the n. So by the time we have like 100 quantum bits, it's 2 to the 100, which is an extreme amount of classical bits. So that basically shows the power of quantum computing, why it's so much better than classical, in the classical sense. Yeah, so exactly what I said here. For the classical one, these 2 numbers determine the state. It's either 0 or 0 or 0 or 1, or etc. But for the quantum one, everything is what's called in a superposition. So everything is basically entangled with another. So you need 4 separate numbers to determine which state it's in. Okay? And another major difference between quantum and classical is that quantum is what's called probabilistic, meaning you have these different constants. They're like physical constants, so they represent the probability of finding our particle, let's say, in this state. So for example, let's say like alpha is 1/2. That means that the probability of finding our state in the 0, 0 state is 1/2, which is 50%. For the classical one, you know it, you get those 2 numbers and you know it, determine it. Okay. So now, from bits to electrons, okay? We have the bits, it's basically the building blocks, as I said, and now we want to transition to electrons, which is an actual application of what we have. And for an example, I talked about phosphorus. So now imagine like a whole transistor, and I'm going to talk about transistors later, but imagine a transistor which is basically made up of a gate, like a source, like an electric source, a gate, and a whole bunch of silicon atoms, okay? Whole bunch of silicon atoms. And inside those silicon atoms is 1 phosphorus atom, okay? And now, phosphorus atoms, on its outermost electron shell, has 1 less valence electron than silicon. So, the silicon atoms, they actually can move back and forth between the phosphorus and the silicon, like they could flow.
The silicon electrons,
Yeah.
not the atoms.
No, not that, sorry. So, when we put this phosphorus inside our system, and we put like a magnetic field, and usually we could get magnetic fields from like a superconductor. So, superconductor gives us a magnetic field, and then the atom is normally in spin down, which means it's in the 0 state, because you need some energy to go to spin 1. And that energy is supplied with the superconductor. So when you turn on this magnetic field from the superconductor, the atoms will align. I mean, the phosphorus atom will align its magnetic dipole moment, which all atoms have. It's like an intrinsic quality of them, and it's going to align with the magnetic field. Okay? Now, it's a bit fuzzy because the atom, as I said before, I mean the electron, as I said before, is basically in a superposition of spin up and spin down. So there's a probability that it's up and a probability that it's down. And the only way we could determine it is if we actually make a measurement. Like if we actually measure if it's in spin up or spin down. But if we don't measure it, then it's all probability based. So there's actually quite a big problem with making a quantum computer, in that when we make like a quantum computer or a quantum processor, there cannot be any interference from the surroundings, which is thermal energy. Because one like a little hint of thermal energy and the whole system is going to go bizarre. So we need to like cool it to like very, very small temperatures where there's no more thermal energy, no more interference from the surroundings. But at this very cold temperature, almost absolute zero, actually, talking about this, people in different labs around the world, they got the temperature to be like 0.00001 times absolute zero, which is pretty close. So thermal energy is basically, it's not there anymore. But there's actually a big problem, not a problem, but like, there's a consequence in that the electrons still move because of what is called the uncertainty principle. It basically says that if we have any change in position, so say that I move the electron a little bit, and change in momentum, then the product of them has to be greater than h bar over 2. Now, there's another condition on that. It says that, sorry, never mind, I'm not going to talk about that. What this is basically saying is that even at such small temperatures, we still have some delta x. We still have some movement because it has to be greater than h bar over 2. That's just basically what we're saying. So what I'm trying to do in my lab, not really a lab, but like experimentally, is use dipoles instead of a phosphorus electron. So dipoles basically, you have, say we take a silicon, okay? And a dipole means on the left side of it is positive, and on the right side of it is negative. It's dipole, it's polarized, you could say. And then some of the benefits are that what is called trapped ions and longer coherence times. Meaning that if we turn on like a magnetic field and a source, it's going to have a long coherent time, meaning that it's going to interact better, and it's going to interact for a longer time. Because as I said again, thermal energy is a big no-no. So this is the setup basically. This is the transistor that I was talking about, and this is the gate. Now gate is basically like, it's a boundary. You get a source, you get like a current from the gate, and it goes through this, and then it's going to allow for the flow of electrons. So you have one phosphorus dipole or silicon dipole in the middle, and then around it is a completely other atom, okay? And then what this point is called a source. You get an input here, and here's a drain. Now over here, these are the boundaries, okay? So the boundaries are important because at the boundaries, this is what is called well, basically, you get like a diffusion. Because remember, I said silicon had one more outermost valence electron, so it could flow better. I mean, it could flow from the silicon to the phosphorus. And silicon here could flow from the silicon to the phosphorus. Okay? So basically what we're going to do is insert the dipole pairs into the silicon crystal with a transistor, and then we're going to apply a superconductor. And superconductor is what's going to give us our magnetic field. The magnetic field is going to make the phosphorus atoms, we're going to make them line up, their magnetic dipoles line up, and that's how we can generate a qubit. And we're going to cool them to very low temperatures using liquid helium. And then the microwaves that you see over here is basically when the phosphorus is aligned, we can send a microwave with the same resonance frequency as the same frequency that is in resonance with the phosphorus, and we can get results from that. So that's all good. That's experimental work. What I have to do is basically do all the math. So I have to do all the math, and this is the essence of what I'm doing, is this funky equation over here. So this psi over here, it's a Greek letter. It determines the state of what we're doing. So psi can be 0, 0, it's in the 0, 0 state, 0, 1, 1, 1, 1, 0. Psi just determines the state. And over here we have what's called H. And H is called an operator in quantum mechanics. Now what an operator is basically something we apply to the system, and when we apply it, we get a result. So when we apply this H operator, it's also called the Hamiltonian operator. We apply this Hamiltonian to our state, say 0, 0, and we get lambda. And lambda is called the eigenvalue. Lambda is the energy. And when we have a system, a quantum system, the energies are going to be quantized, meaning there's discrete amounts of energy. You can't just have any energy. They're basically discrete amounts of it. So we operate our Hamiltonian on the system, and it gives us the energy output of the system. Now you have, what I'm dealing with is two dipoles. So they have an angle between them. Okay? And this angle is what we want to optimize. So we want to optimize the angle to get the highest energy. If we have the highest energy, highest lambda, then we know that we have optimized the angle theta between the two dipoles. Because they can be arranged in any way, but we want to find this optimal angle. Okay? And then after we do that, what I'm going to do is find the time evolution. And to find the time evolution, we have another operator, which is u. We operate u on our state, say 0, 0 again, and when we operate it, we get the time evolution of the system, how the system acts over some time interval. And that could be useful also. And then, compared to a traditional method, without the dipoles, we want to find this error approximation. And basically what the error approximation is like the difference. Because when we have an angle theta with the dipoles, it's going to be a little bit approximation compared to the usual way of doing it. Okay? So I basically have to do all the math, verifying and optimizing the experimental procedure.
You said you wanted to create a qubit. Is that your goal, or has it already been done?
No, qubit has been done. Actually, they made a system with, I believe, like 512 qubits, which is pretty good. Yeah, so that's not my goal. My goal is basically to make a quantum processor using another method. Because usually they just stick a phosphorus in there, but what I'm proposing is use dipole.
Like dipole, meaning like the spin of the electron.
No.
But that's not what you mean.